Myself, Dr. Koteeswari, Department of Physics, and today we are going to discuss about the synthesis of nanomaterials. And in synthesis of nanomaterials, we have a top-down, a bottom-up approach: ball milling, gas phase condensation, vacuum deposition, physical vapor deposition, thermal evaporation, and chemical vapor deposition. Now, in this, we'll discuss one by one about the synthesis of nanomaterials. And before going to this, we need to understand what is nanomaterial and how do we synthesize those things. And nanomaterials are nothing but the size reduction. Initially, for example, we have the centimeter we used to discuss in 10 power minus 2 meter, and the millimeter as 10 power minus 3 meter, and the micrometer in 10 power minus 6 meter. In case of the nanomaterial, nano means we all know that it is in the 10 power minus 9 order. We are going to reduce the size with the use of these synthesis materials to 10 power minus 9 meter. Then the nano material synthesis part is, 1 minute. Nanomaterial synthesis refers to many materials which creating nanoparticles. It can be synthesis from the bottom up methods, or for example we can take the nucleation, and in nucleation how the nucleus are distributing, and the nucleate and grow the particles from fine molecular distribution and from liquid vapor deposition. And this is the basic structure of today's class. The nanomaterial synthesis method, we have the top down and bottom up approach, and in top down approach we have the physical methods. Under that we have the mechanical method, physical vapor deposition, lithography and thermal evaporation. In case of the bottom up method, we have the chemical methods, biological methods. In our syllabus we discuss about the chemical methods, that is the sol gel, chemical vapor deposition, co-precipitation and hydrothermal and microwave, so on. And the biological method is just for your reference, I have mentioned here. These are the using plant extract we can do it in the project. And these are the basic thing what we are going to discuss on today's class: the nanoparticle synthesis, the mechanical method, gas phase methods and liquid phase methods. In mechanical method we discuss about the grinding or milling, and in gas phase methods we discuss about the chemical vapor deposition and physical vapor deposition and laser ablation. And in liquid phase methods we discuss about the hydrothermal synthesis, sol gel for fabrication and so on. And this slide explains us how the top down and bottom up approach has taken place in case of a nanomaterial synthesis. And here the diagram shows us the bulk material is synthesis to the powder material, that is, again it is synthesis to the nanoparticles. And in the right hand side you can see the green color clusters of atoms. Here initially we take up the atoms and it is made into the clusters, and it is again made into the nanoparticles. For example, you can take a brick and you can cut the brick into the small pieces. So you can consider the brick as the bulk material, and when you with the help of the hammer you can cut the brick into the small powder. You can keep that in your mind, that is the top down approach is like this. And in case of the bottom up approach, you take a powder like material, and the powder like material is mixed with some water, and it is made into the bulk material. And this diagram explains you how the bulk material is transformed to the nanoparticle size material. And initially the orange color bulk, it is named as bulk there, and that is due to the transformation of energy, the bulk material is divided into the cutted into the small pieces like circle like orange material. And in there what happens is the transformation of small fragments taken place in the powdered form. The powdered form may be in the multi-layers or mono-layers. Now coming to the bottom-up approach, the nanomaterials are taken. Initially the powdered form is taken and it is gone to the cluster form, and again to the ionization by the energy, it comes to the condensation of the clusters. Then the nanoparticle synthesis are made. This is the reversal process of the top-down approach to the bottom up. Top down is the reversal of bottom up, bottom up is the reversal of top down approach. And here I have given you some of the examples of the top down approach and where we are going to use the top down approach, and what are the uses of, and what are the examples here we come across in our daily life. Those are very important to know, girls. And here the integrated circuit fabrication is mainly used in the top down nanotechnology. It has been grown to the level of the fabrication that we call it as the NEMS, where NEMS is nothing but the nano electromechanical system. In this, we take up the tiny mechanical components like levers, spring and fluid channels, and along with some electrical circuits embedded with the tiny chips. And the examples of the top-down approach is I have mentioned here, the colloidal dispersions and etching of typical top-down methods, and this is also the main thing we use in our daily life. I tell you later. And here this slide gives you the what are the advantages and disadvantages of the top-down and bottom-up approach. So mainly we use for the chemical purification. Top-down approaches can be used for the chemical purification, whereas the bottom-up approach can be used to size the narrow size distribution is possible in case of the bottom-up approach. The disadvantages over here is, in case of a top-down approach, it is very broad in size, that is 10 to 1000 nanometer, and the impurities are in the range of the stresses, defects and imperfections get introduced, and it is more expensive when comparing to the other approaches. And in case of the bottom-up approach, we can produce it in the large production. That is, the large production is very difficult in case of the bottom-up approach, and the chemical purification of nano particles are much required. But we cannot do the chemical purification in case of the bottom-up approach, because when we mix up with some molecules, there may be some impurities present, so that it can change the base component itself. Now coming to the ball milling is nothing but the grinding method that grinds the nanotube extremely to the powdered form. Usually we can take up the ceramic and the stainless steel also used for this case. And during this ball milling process, the collision between the tiny rigid balls in the concealed container will be generated with the eye pressure. With the help of the eye pressure, it can be easily milled like the machine is grinding our rice powder and the wheat powder, like that. The same process is taking place here in case of the ball milling. And the basic mechanism of the ball milling is nothing but we are going to rotate it in the horizontal axis and partially filled with the material and to the ground plus the grinding medium. Then the diagram is given over here. Here now look at the diagram. Here it is the circle-like diagram, and in this the shell, the nanoparticles are initially poured into it, and the ball milling works on this impact and attributions. Here what we are going to do is the size reduction is done by the impact of the balls to the near of the top of the shell. So in this shell again we are going to fill up the materials, then again the rotation will be taken in the horizontal axis, then the materials will be grinded into a powdered form. Then here I have given the principle why we are going to use the ball milling is nothing but to get the size reductions of the impact of the balls near to the top of the shells. Then where we get the smaller size ball means at the top of the shells we will be getting. And here the constructions, in constructions we have the, I have given you the what type of range should be taken, and the how much percentage of the volume should be taken inside the sphere like shell, and how many balls can be taken up, that is in the range 12 millimeter to 125 millimeter can be taken. And the how the shell is rotating, initially I have told the shell is going to be rotated with the filled balls, and finally we are getting the powdered form. And how the rotation must be, the RPM is nothing but rotation per minute. How the rotation is taking place means that is 60 to 100 RPM, and large mills shells might be in the diameter of 3 meter in a diameter and 4.25 meter in the length. and this operation is continuously taken up until the material is taken to the powdered form. And here the working of the conical ball mill is I have given here, and in this case we can increase the speed and also the feed also we can increase, because in case of the sphere like ball mill we can use only 10 to 20 balls, and here we can increase the feed and also the capacity of the outcoming fineness of the powder also increased. And why we are using this? What are the applications of this ball mill means? It is used to get the material like coal, pigments and pottery, and grinding can be carried out either in any of the form. It is not mentioned that it should be only in the wet form or in the dried form. And for production of the amorphous material mainly used, and the chemical reactivity also in case of the ball mill is more effective when compared to the physical reactivity. And these are the advantages of the ball mill. The cost of installation is very low. We can make installation this in our lab itself. The cost of production is also very low in such materials of all degree of hardness, and the grinding medium is also very cheap, and it is suitable for the continuous operation. We can continuously do this without any interruptions. And there are some disadvantages here. The rotational of the ball loading is very difficult. Mill efficiency is very low, and the feeding size is also wide and not easy to get thinner and end product. In this case, the thinner product we cannot get as a end product. After getting the product, again we need to grind it. Now here we have some of the other methods like gas phase condensation. In this gas phase condensation, the reactance takes place due to the temperature increase and supersaturation is created. For example, we take up the iron nanoparticles here, but here also we come across some of the general issues. The temperature we need to maintain 10,000 Kelvin, and some problems in the liquid phase is prevented, and the gas phase condensation conditions of the properties of the nanomaterials cannot be controlled as much as possible in our lab itself. But that is the manufacturing techniques like flame, hot wall and plasma and laser evaporation reactants are some of the basic issues we come across in case of the gas phase condensation methods. So hence we shift on to the vacuum deposition. In this the vacuum deposition is taken place with the help of the evaporation, and in which the atoms or molecules are evaporated from the source thermally, travel without collisions with residual gas molecules in the deposition chamber. And the basic definitions of the physical vapor deposition is the process used to produce a metal vapor that can be deposited on electrically conductive material as thin as highly hardened pure metal or alloy coating. In this, the vacuum pressure they have taken is 10 to 6 torr using the cathodic arc source. And in the vacuum vapor deposition is carried out with the condensation and evaporation of the material, and it is used in the high melting point and low vapor pressure, and also it can be carried out in high temperature and vacuum. And this is the physical vapor deposition, how it takes place. Initially look at the diagram. From the source solid to liquid, what happens initially I told you it can be in the evaporation mode. So with the help of the evaporation, the solid source is converted to the gas phase, and the gas phase is transported or deposited with the solid phase. And here what happens is the high temperature vacuum evaporation with the subsequent condensations or plasma is settled on the material, and no chemical reactions are taken place in this, used for the uniform and thin coating or film. Next, we discuss about the thermal evaporation. It is the straightforward in means of the thin film depositions with the material. Here we use the temperature up to 1700 degrees Celsius. And this is the diagram of the vacuum phase deposition, and here in the vacuum chamber is kept, and the crucible, the red color is here, it shows the pumping system, and the vapor flux and substrate is kept there. And here what happens, how does it works is, the thermal evaporation is the very oldest, and it is very probable in the range of the 0.1 to 10 milli Pascal, and it is greater than the chamber dimensions. That is the main advantages over here. And where we use those things, the thermal evaporation in the tungsten flame and the sheet board sources and the crucible sources like this. So here I have mentioned some of the examples. The chemical vapor deposition is the coating what we are doing on the thermally induced chemical reactions at the surface of the heated substrate. And this technique, with the help of this technique, on the formation of the gaseous state, it containing the coating element with the coating retro to the or to the chamber. Alternately, we can use the gaseous spaces may be generated on external to the coating reported to the introduced via the delivery system. Here it discusses about the chemical vapor deposition, and already I have told you the chemical vapor deposition comes under the bottom up approach. So bottom up approach is nothing but initially the precursor is taken, and the gas is sent to that, and it is with the help of the vaporization it goes up, and in the chamber you can look at the molecules or atoms are present there, and it undergoes heating, and after that it settles down on the collector. Here this slides explains you about the chemical vapor deposition and physical vapor deposition, and this slides explains you about the chemical vapor deposition and physical vapor deposition, and the advanced thing I have given it on the right hand side. And the sol gel technique, the one of the most important technique which we can use in our lab itself. And in this, this is the process of settling of the nanometer size particle from the colloidal suspensions. And here we can take any metal alkoxide which can be dissolved in the water or alcohol, whatever may be the dissolvent component we need to check out, and we can use water or either alcohol, and it can be converted into the gel form by heating and stirring by the hydrolysis. And this diagram explains you how the sol gel process is taking place. Initially the precursor, that is the base material or the solvent we used to call it as, it is taken in a beaker, and the sol formation is taken up, it shows in the orange color, and the connected porous structure, it forms like a gel form. The gel form is shown in the blue color. And here what happens, it divides into the three categories, that is the supercritical drying and thermal drying and freeze drying. In case of a supercritical drying, it goes on to the aerogel state, and when we dry those in the thermal drying, it goes on the xerogel, and when we freeze it, it goes on the cryogel. And in any of the form we can get the final product as a powdered form. And here we call it as the initially the step 1 as the hydrolysis, and next condensation. After that the drying agent we can call as aging or drying, and the final product we take it as a step 5, that is the calcination. And here some of the advantages I have given here. It can be used to prepare the material with a variety of shapes such as porous structures like thin fibers and dense powders and thin films. And the size ranges are from 20 to 200 nanometer. Initially I told you the nanometer size must be in 10 power minus 9 meter or 10 power 10 nanometer. but here we get up to 20 to 200 nanometer. That is, in the order we get 10 power minus 9 meter. That is the main thing for us. In case of the sol gel technique, we can produce the nano powder material in case of up to 20 to 200 nanometer. And here also we come across some of the disadvantages, that is the gel forming process takes 2 or 3 days also. For some compounds it can form in 2 to 3 hours, which makes the gel timing consumption, the fabrication technique compared to the other methods, it is very difficult for us because we need to wait for the gel formation. And here this picture explains you the advantages and disadvantages of the sol gel technique, and it is a long process time, high cost of raw materials are needed for this. Those comes under the disadvantages, and advantages is it is the low process, the temperature, high purity, and the production of organic and inorganic hybrids can be developed with this process. Thank you.